Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 56, and it is entitled Parallel Circuits. We are looking at a second way of connecting various elements in a circuit together. And we care about this because it turns out that more complex circuits can be thought of as composed of combinations of series circuits and parallel circuits. We've already looked at series circuits. In this lesson, we look at parallel circuits. Let's remind ourselves of what we know already about series circuits. In a series circuit, we have all the resistors connected in line with each other. The total current is equal to the current through each of the resistors. Mathematically, we say that IT is equal to I1 is equal to I2 is equal to I3. This current equivalence is a statement of common sense. I cannot have charge pile up in the circuit somewhere so that the rate at which charge flows through each of the resistors must be the same. The total voltage drop across each of the resistors must sum together to be equal to the EMF of the battery. And the way we express this is we say that E is equal to V1 plus V2 plus V3. So in this diagram on the right, this resistor here, RS, is supposed to take the place of these resistors on the left here, R1, R2, and R3. What is the relationship between those? What we found in Lesson 51 is that RS is equal to R1 plus R2 plus R3. Now we want to discuss parallel circuits. Let's sketch ourselves parallel circuits and come up with similar sorts of statements about current, voltage, and equivalent parallel resistance in a parallel circuit. You can see that in a parallel circuit, the resistors are connected so that each terminal of the resistor is touching each terminal of the other resistor. In other words, the current that approaches each branch in the circuit has to split between each of the resistors. What you should see is that the battery is going to send current, which I'll call IT, a total current, through the wires that are connected to the terminals of the battery. But as the current approaches these different junctions, one of them indicated here, then some of the current is going to split off, and we're going to call the amount of current that flows through the first leg, we'll call it I1. And then as the remainder of the current approaches the second branch, then some of it's going to split off again. We'll call that I2. And then the remainder of the current that flows is going to pass through this third resistor here. Those currents are going to recombine somewhere at this junction and at this junction, so that what ends up happening is that I'll have a total current flowing back through the battery. What I want you to see is that the charge that goes through resistor 1 is not available to go through the resistor 2 or resistor 3. And likewise, the charge that moves through any of those resistors can't pass through the other resistors. That is a characteristic of the parallel circuit. So we can write down our current relationship. By common sense, we see that IT has got to be equal to I1 plus I2 plus I3. Now what about the voltage? Remember what we mean by voltage. The voltage is the amount of energy per charge that the circuit possesses. What happens is that as the charge passes through a device like a battery or a resistor or a motor or anything else that's other than an ideal conductor, the amount of energy that the charge possesses is going to change. That charge is going to deliver its energy to whatever circuit element it passes through. Things that are connected together by ideal conductors, which is what we're considering wires to be, all possess the same amount of energy per charge. And the way I'm going to try to illustrate that is to show, using color, the potential of each part of the circuit. I'm going to start on the high potential side of the battery, and I'm going to indicate it with a red line. In a similar way, I'm going to show the low potential part of the circuit with a blue line. What we would say is that there is a difference in potential between the terminals of the battery. That difference in potential is equal to the EMF E. Now, any ideal conductor, which is what these connecting wires are, that are connected to the high potential side of the battery are going to allow charge to pass through without losing any energy. So we would say that those wires on the high potential side of the battery have the same potential as that terminal of the battery. So I'm going to color those wires red. Every wire in the top part of this circuit has the same potential as the high potential side of the battery. In a similar manner, we can look at the low potential side of the circuit. Any connecting wire that's connected to the negative terminal of the battery is going to have the same potential as the negative terminal of the battery. So I'm going to color those wires the same color as the low potential side. They're all going to be blue. So I'm using color in this circuit to indicate the electrical pressure that's in the circuit. On the high potential side of the battery, all of those things are at high electrical pressure. And on the negative side, the ones that are all colored blue are at low electrical pressure. The difference in the colors indicates something about the difference in the electrical pressure. And what I claim is that the difference in the electrical pressure, the difference in potential across each of those resistors is the same as what's across the battery. In other words, the EMF of the battery is the same as the difference in potential across R1 and across R2 and across all R3. And that gives us our voltage statement. That statement is that the voltage drop across each of the resistors in parallel is equal to each other. Now you'll notice that these voltage and current relationships are for a parallel circuit are different than the ones in the series circuit. We have one more that we need to derive, and that is what is the equivalent parallel resistance. Let's suppose that I took and built a circuit that had a single resistor that I'm calling RP, and that resistor would take the place of these resistors over here, R1, R2, and R3. What is the equivalent parallel resistance? Let's start with our current relationship and derive it. But now let's recall Ohm's law. Ohm's law says that I is equal to the voltage divided by the resistance. So I could write that for each of these things. In this circuit that we've drawn over here, I could say that the total current, IT, passing through is going to be equal to E divided by RP. In a similar way, we could say that the current that passes through R1 is equal to V1 divided by R1. And likewise, for I2, it's V2 divided by R2, and for I3, it's V3 divided by R3. But now let's remind ourselves about how the voltage is related. E and V1 and V2 and V3 are all equal to each other, and they all appear in the numerators over here on our resistance relationship. So I can factor those things out, and what I'm going to end up with finally is our parallel resistance equivalent. So let's add this equivalent parallel resistance formula to our list. These three equations for parallel resistors are going to be important as we solve problems. In the circuit shown, determine A, the total resistance RT, B, the total current IT, and C, the current through R2. So both of these resistors experience the same difference in potential across them. I want you to see that the voltage drop across R1 and the voltage drop across R2 are each 20 volts. Let's begin by finding the total resistance. I'm going to sketch the circuit again and show the single parallel resistor replacing these two. This is a parallel circuit, so that 1 over RT is going to be equal to 1 over R1 plus 1 over R2. So now I can just put in the numbers. I find that this equivalent resistance has a resistance of 2.4 ohms. Here is something that you will see as a characteristic. The total parallel resistance is going to be less than any of the resistors that make it up. And that makes sense. When I branch the circuit, I'm allowing alternate paths for the charge to pass through. So it's easier for the charge to pass through a parallel circuit when I have more and more paths. That means that the total resistance drops. Part B says to find the total current. Well, I can say that the total current is going to be the total voltage divided by the total resistance. So I can just put the numbers in now. I get that there's 8 1/3 amperes total current that is flowing through the battery. Finally, we want to figure out what's the current through R2. There's going to be current that flows through resistor 2, I'll call that I2, and current that flows through resistor 1 that I call I1. There is a total current that flows out of the battery and back into it that's equal to this 8 1/3 amperes. That's what we calculated in part B. Now, when that current gets to this junction here at the first resistor, part of it, I1, goes through resistor 1, and the rest of it, I2, goes through resistor 2. How much of it passes through resistor 2? Well, one way we could figure that out is to take I2 and say that's equal to V2 divided by R2. But we know that V2 is the same as the EMF. It's 20 volts. And I get 3.3 repeating amperes is the current through resistor 2. Let's see if that makes sense. If this is 3.3 1/3 amperes, then the remainder of it, I1, would be 8.3 minus 3.3, which is 5 amperes. Is that what I would get if I took 20 volts and divided it by 4 ohms? It sure is. So this checks out. In the circuit below, determine A, I2, the current through R2, B, IT, the total current, C, R1, and D, PT, the total power dissipated by the circuit. I want to begin because this circuit looks a little bit different than the other ones that we've seen, but I want you to see that R1 and R2 are actually in parallel with each other. And so what you'll see is that these connecting wires are spreading the electrical pressure out throughout the whole circuit. And likewise, on the negative terminal of the battery, I have blue, so that the difference in potential across R1 and the difference in potential across R2 are the same, and they're equal to 24 volts. That's 0.24 amperes. That's what I2 is. Part B says find the total current. Well, they tell us I1 is 0.45 amperes. We just figured out what I2 was, 0.24, so I could figure out the total by adding those together. IT is going to be I1 plus I2, which is 0.45 amperes plus 0.24 amperes. And when I put that together, I get 0.69 amperes. That's the total current through the battery and through both resistors together. Part C says, find the resistance R1. I can use Ohm's law. R1 is going to be V1 divided by I1. And since I know V1 is 24 volts and I1 is equal to 0.45 amperes, then I can put that into my calculator. Finally, we're looking for the total power dissipated by the circuit. I'm going to use one of the power formulas. Since I know what the voltage is in the circuit is 24 volts, and since I know what the total current is, then I could say that the total power is the total current times the total voltage, which in this case is the EMF, 24 volts. I'll put that into my calculator. I get that the total power dissipated by the circuit, the total power that's produced by the battery, is 16.56 watts. So, for this lesson, what we've done is we've established the relationships for parallel circuits, for voltage, current, and equivalent resistance. In a previous lesson, we did it for series circuits. In a future lesson, we're going to put it all together and get into mixed circuits or complicated circuits. But for now, that's it.